Okay, so we have a quiz today. It feels like we have had a lot of tests and stuff, but this is the end of that long stretch. So, yeah, that's been too much. Sorry about that. So we ended last time with this example. That's how you draw a helicopter. And the helicopter was moving 15 meters per second. That was its speed. (20 degrees below horizontal. And when the helicopter was 30 meters above the ground, an object is dropped. And so there are two questions. How long does it take for the object to hit the ground? And then second, how far horizontally does the object travel from when it's dropped to when it hits the ground? Okay, so if this is a picture of when it's dropped, this distance is 30 meters. We have to choose those four things. We have to choose an instant for time equals 0, an instant for time final. Bless you. The origin location, and a coordinate system orientation. For time equals 0, we're going to choose when the object's dropped. For time final, we're going to choose when it hits the ground. For the origin location, I'm going to do what I usually do. Put the origin on the ground, right beneath where the object is at time equals 0. So on the ground, right below where the object's dropped. And then this is my coordinate system orientation. So the y-axis, oh, I didn't write this. So origin location is on the ground. Right beneath the drop point. And the coordinate system orientation has the y-axis up. That means the x-axis has to be horizontal in some way. So the x-axis is horizontal, and we'll put it in the direction of motion. And now we have to think about what we know and what we want. Do we know time final? No? Do we want it? Yep, that's the thing we want. Do we know anything about acceleration? Yep, free fall, so we always know those. So AX is 0. AY is negative 9.81. Do we know anything about initial position? We do. um, so this is a picture of what's going on at time equals 0. This is a picture of what's going on when the object's dropped. So what you're looking for is the position of the object as a set of coordinates in this coordinate system. What's the x-coordinate of that point? 0. Yep. So that's PIX. And what's the y-coordinate? 30. Yep, positive 30. Do we know anything about the final position? We don't know the horizontal component, but we do know the vertical component because our time final is when it hits the ground, and the ground is our 0, the ground is our 0 y position. The origin is on the ground. So we know that PFY is equal to 0. We don't know PFX. Do we know anything about the initial velocity? Yeah, we can get that from this information. We know that it has a speed of 15 meters per second, and we know that it's at an angle 20 degrees below the horizontal. So VIX and VIY, we're going to get those from taking this vector, which we know has a length of, what did I say, 20, 15? 15 meters per second. And we'll put the tail of this vector at the origin of the coordinate system. And we know this angle is 20 degrees. And now you need the counterclockwise angle from the x-axis to the vector. You can go all the way around and use positive 340. Or you can go the short way around, use negative. So this would be negative 20 degrees or positive 340. And so the velocity vector is 15 times the cosine of 340 and 15 times the sine of 340. Which is 15 times the cosine of negative 20. These are the same thing. 15 times the sine of negative 20. And if you calculate that, I don't know. Can someone calculate that? 14.095, okay? Negative 5.13. So VIX is 14 point, let's call it 10. Yes. So once you get to this point, it's like those practice problems in the vector set. You're always just trying to, so the first thing you have to do is figure out an angle. And the angle comes from going counterclockwise from the positive x-axis to the vector. And you have to put the vector's tail at the origin. So if you go counterclockwise around to here, you could think of it as 360 to get all the way back, but then you have to backtrack 20 because you didn't make it quite that far. So that's 340. And then you just, it's always going to be cosine of the angle, sine of the angle, just multiplied by the length of the vector. So in this case, it's 15 times the cosine or sine of 340. You could go clockwise too, and then you just have to call it a negative angle. So VIX is 14.10, VIY is negative 5.13. And then do we know anything about the final velocity? Nope. Okay, so is there an equation that works with these? There is one. So I think the one we want is PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared. So 30, nope, try that again. 0 is equal to 30, excuse me, plus negative 5.13 TF plus 1/2 times negative 9.81 times TF squared. So 0 is equal to 30 minus 5.13 TF minus 4.905 TF squared. That's a quadratic equation, and so you can use the quadratic formula with this A, this B, and this C. And can someone tell me what the roots are for that? Okay, so these are the two roots. With time, it's easy to, if you have one positive and one negative, it's easy to figure out which one you want because we don't use negative times. So we want this one, and we don't want this one. Yep.
Can you do the quadratic formula, please?
Like, you want me to write it out?
Yeah.
Sure.
Or teach us how to do it in our calculators.
Yes. In your calculators, if you don't have it programmed in, talk to me during lab, and if we have time, and I can program it in. But so what you do is you have a number multiplied by the variable squared, and that's what you call A. So for us, that's negative 4.905. You have a number multiplied by the variable, that's B, and then you have a constant, C. And the quadratic formula says negative B plus or minus square root of B squared minus 4AC all over 2A. So you just plug those numbers into this formula, and it'll give you two answers because of the plus and the minus. And in this case, we want to take the positive one.
But for, like, when you square 5.13
Mm-hmm.
and it's negative?
No, actually, so that's an important point. You don't do that. You think of this whole thing as in parentheses, and you square all of it. So you have negative 5.13, and you square that, which that negative goes away, and you get like a positive 26 or 25 point something.
Okay.
And yeah, so think of all of these as being in parentheses. Okay, so that's TF. That's how long it takes for this to hit the ground. And now we want to figure out horizontally how far it travels in the air. Is there any reason to change any of those four choices at the beginning? Nope. Really, the only reason that you would ever change those is if you're now asking a question about a different instant in time. But we're still asking a question about when it hits the ground. So choices stay the same. And if all the choices stay the same, everything you knew before, you still know. So if you think of what we know and what we want, We still know all the old stuff. And we know now also that TF is equal to 2.01 seconds. And what we're looking for is PFX. Okay, so if you know all this, and you also know TF, and you're trying to find PFX, is there an equation that works with those? The same one, but the x component. So we can use this equation. PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared so PFX is equal to 0 plus VIX was 14.1. So plus 14.10 times 2.01. And then what's AX? AX is 0, so this goes away. And what do you get if you multiply 14.10 and 2.01? 28 point what? Okay. So PFX is equal to 28.33 meters. Any questions about that one? Let's do one more. So this one, remember the example that we did where I drew the picture of the guy with the gun and the guy who dropped the bullet? And those took off at the same instant. And surprisingly, they both hit the ground at the same time. And we watched the video, and that's how it works out. It's surprising. But for that to work, it depends on the gun being shot exactly horizontally. If it's not, there's some y part of the velocity, some vertical part of the velocity that changes everything about the times. So what we're going to do now is a problem where a gun is shot horizontally. Well, let's think of it this way. Let's think of an object that's dropped from a meter high, like a bullet, and we'll measure the time it takes for it to hit the ground. And then we'll think of a gun that's shot not quite horizontally, but some small angle up, let's say 1 degree up. Let's say it's basically horizontal, but it's aimed up a little bit. Do you think it's going to take longer or shorter to hit the ground, or the same, or what? Longer. It's going to take longer. And because a bullet goes really fast, the difference is going to be surprisingly big. Okay? So a bullet dropped and shot from the same height, but the bullet is fired 1 degree above horizontal. So that 1 degree change will make the bullet take a lot longer to hit the ground. Okay, so Step 1. Let's say that this bullet is just dropped. It's a big bullet. I'm not getting into that again. I blame that mostly on you. Okay, so step 1, drop the bullet. And let's say that the distance that it drops is 1 meter. How long does it take to hit the ground? Okay, so first we have to choose these 4 things. Time equals 0, time final, the origin location, and the coordinate system orientation. By the way, we're doing this as a 2D problem, but if you're just dropping this bullet, it's motion along a line, really, and we could also just think of it as motion along a line. Either one of those 2 approaches will work fine. So time equals 0 is going to be the instant it's dropped. Time final is going to be the instant it hits the ground. The origin location is going to be on the ground beneath where it's dropped. And the coordinate system orientation is like this. So the y-axis is up, x is horizontal. It turns out we're not going to use any of these x variables, but let's say it's horizontal the way the guy is facing. Okay, do we know TF? Nope, that's what we want. Do we know anything about acceleration? Yes. So AX is 0, AY is negative 9.81 meters per second squared. Do we know anything about the initial position? So what's PIX? 0. And what's PIY? Yep, positive 1. Do we know anything about the initial velocity? What is it? Yeah, it's dropped, so VIX and VIY are both equal to 0. And do we know anything about V final? No. All right, is there an equation we can use with these to figure out time final? I think it's the one we keep using, right? Oh, I did skip one thing that we know. In here, we do know something about the final position. We know PFY is equal to 0 because the origin is on the ground. So when the thing hits the ground, PIY has to be 0. Okay, so PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So that says 0 is equal to 1 plus 0 minus 4.905 TF squared. So positive 4.905 TF squared is equal to 1. So TF squared is equal to, what's 1 divided by 4.905? 0.2038. And then take the square root of that, and time final is equal to plus or minus 0.45? And then this is time, so we're not going to ever use the negative one, so we'll take the positive. Okay, so that's how long it takes if you drop a bullet from a meter to hit the ground. Okay, and now we're going to do the calculation where a bullet's shot from just an angle of 1 degree above the horizontal. It would be almost, that's almost too little of an angle for you to even be able to see, but we're going to see that it has a big effect on the time that it takes. Okay, so this time I'm drawing a normal sized gun. No need for comments. And it's an angle of 1 degree above the horizontal and a speed of 500 meters per second. How long does the bullet take to hit the ground? Okay, take a few minutes and see if you can work through this one. You can work together, compare answers, talk out loud, dance, sing, celebrate, ask me questions. Yeah, all at once. Perfect. Yeah, if you get stuck, ask me questions too. But the thing we're trying to do here is you want to see, like, I'm going to do the problem afterwards, and you want to see if there's a place where something went wrong with your understanding so that then you can go back and figure out what you were missing. Okay? Yes. So the origin location, it's your choice, just like the 0 position was your choice with motion along a line. And just like that, it's arbitrary, so you can do it no matter what you choose. It's just a way to be consistent through the problem. But you don't have to be very creative about it. I think if you just always choose, like, think of the bottom of your problem, the ground or the water or whatever the bottom of your problem is, if you can always just put the origin on that location underneath the object at time equals 0, you know. So in this case, then you would put the origin on the ground right beneath where the bullet was fired.
I'm just trying to connect the dots on why it's called origin, because it seems like if you're looking at this picture,
Mm-hmm.
the origin is like the beginning. So
Oh, okay. Yeah, that's a good question. So I mean origin in the sense that it's the coordinate system origin. So it's 0, 0 of the coordinate system. You're just deciding where to put the coordinate system. So you can think of choosing the coordinate system is in 2 steps. You decide where to put it and you decide how to orient it. Yep. Shut up. Okay. That's more like it. Okay, so time equals 0 is when it's fired. Time final is when it hits the ground. The origin location, I'm going to do what I seem to always do, put it on the ground, right beneath the object's location at time equals 0. And then I'm going to orient the coordinate system with the y-axis up and the x-axis horizontal in the direction of motion. So the origin location is on the ground, beneath the bullet at time equals 0. And the coordinate system orientation has the y-axis up and the x-axis horizontal in the direction of motion. Do we know time final? Nope, that's what we're looking for. Do we know acceleration? Yep. So AX is 0. AY is negative 9.81. Do we know P initial? Yeah, so in free fall problems, as long as the y-axis of your coordinate system is up, these are just always the answers. So you have an acceleration down and nothing horizontal. PIX is 0. PIY is positive 1 meter. Do we know anything about P final? Yep. PFY is 0. Do we know anything about V initial? Yeah, so we have to use cosine and sine for that one. We know that the speed is 500. And if that's an exaggerated angle, but we know this has a magnitude of 500. And if you put the tail at the origin of the coordinate system, we know this angle is 1 degree. So to go counterclockwise from the x-axis to that vector is just 1 degree. So cosine and sine of 1. And what do you get for that? So VIX is 499.9 meters per second, and VIY is 8.7 meters per second. Do we know anything about V final? Nope. Okay, so now we can use this equation again. PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So 0 is equal to 1. Question? Yep, plus 8.7 TF minus 4.905 TF squared. So negative 4.905 is A. Positive 8.7 is B. And 1 is C. And what do you get if you solve that? 1.8 what? You didn't? Oh. Okay, so what else? What are some other numbers? What's the negative one? Okay.
-2.598, and then I got positive 45.42.
That's too big.
Yeah. So, I don't know, can you do the quadratic formula?
1.8. It is 1.89? Okay. Let's do that after if you want. I'd be happy to look at that with you, Tessa, after, but I'm not going to plug that in right now, I don't think. Okay, so not this one. Yes, this one. And so just with that 1 degree change in angle, we went from a time of 0.45 seconds to hit the ground to 1.89 seconds, a huge difference between those two. I have one more comment about this one. So, like all of the examples we did in lab, we were dealing with things. The fastest we were thinking about things is how fast something would get being dropped from 60 feet. And mainly the take-home message was for metal objects, things going that fast, air resistance isn't that big a deal. Like the free fall approximation is reasonable. If we used the free fall approximation to calculate how far away this bullet hit the ground, we would get terrible results. And the reason is that this is going so fast, you know, and that speed messes everything up. But this is kind of the interesting thing, a little hard to wrap your head around. This time, this 1.89 seconds, that time would be almost exactly right. And the reason for that is, remember that the whole idea in the first place of doing that comparison of the bullet dropped and the bullet shot was to point out that the motion vertically and the motion horizontally are independent of each other. And so the horizontal motion, the thing is moving really fast. And so air resistance affects the horizontal motion a lot. The vertical motion isn't moving very fast. It's moving 20 miles an hour. You know, that's 8.7 meters per second is about 20 miles an hour. And so air resistance doesn't affect the vertical motion very much. And so this result is good. Any questions about that example? Okay. There's one more thing that I want to say before we're done with 2D kinematics. So we've thought a little bit about what acceleration means in one dimension, but we haven't thought about what it means in 2D, and it changes a little bit. In both 1D, so that's motion along a line, and 2D, acceleration measures a change in velocity. Acceleration. So if the velocity isn't changing, then acceleration is 0. Acceleration being 0 and constant velocity mean the same thing. That's true in both 1D and 2D. But in 1D, acceleration could only make the speed change. So acceleration only makes things speed up or slow down. In 2D, it does two different things. There are two ways the velocity can change. So in 2D, acceleration does two things. First, it makes things speed up and slow down. But the second thing it does that doesn't happen in one dimension is it also makes things turn. In one dimension, there's no such thing as turning. You know, all you can go is forward and back. But in two dimensions, you can change directions, and acceleration does that. So anytime an object is speeding up or slowing down, it's accelerating. And anytime an object isn't moving in a straight line, it's accelerating. So any turning is an acceleration, okay? Because the velocity vector is changing. So I want to give you a sort of a way to think about that. So to visualize that, think of the path of an object. So let's say the object's moving along this path, and it's going this way. And let's say that it's speeding up. And let's put the object in the middle somewhere. Okay, so first, draw the velocity vector. The velocity vector is always tangent to the path in the direction of the motion. So for this example, a tangent to this path is like this, and the direction of motion means this way. You know, the object's going this way, this is a tangent, and this is a tangent. So you have to choose, is the direction of motion this way or that way, and it's this one. Anyone have any questions about that, finding the velocity vector? Okay, so this is the velocity vector. Second, if the object is speeding up, draw an acceleration, we'll call it A parallel, in the same direction as the velocity vector. And then if the object is slowing down, we'll draw that A parallel in the opposite direction of the velocity vector. Okay, so in this case, is this object speeding up or slowing down? Speeding up, so I'm going to draw A parallel in the same direction as V. Like that. Third, if the object is turning, draw A perpendicular to the velocity vector. In the direction of the turn. So in this example, if you think of sitting on top of this, or you think of a driver sitting inside this ball, is that driver turning left or right to stay on that path? Left. And so A perpendicular is going to be pointed straight to the driver's left. Can you picture what I mean? Or anybody have any questions about that? It's perpendicular to the vector, but there's two choices that are perpendicular. One is this way and one's that way. So you have to figure out which way it's turning. And I'm going to draw that here for the purposes of vector addition. So I'll call that A perpendicular. And then step 4, the total acceleration is the sum of A parallel and A perpendicular. Yeah, but you can put those vectors anywhere, but for vector addition, you have to put them head to tail. That's why I put it there. So the total acceleration goes from, I took these two vectors, I put them head to tail. The sum of those vectors goes from the free tail to the free head. And so this is the total acceleration vector. So that's a way to visualize what acceleration looks like in 2 dimensions. And it's a way to break up the acceleration into a part that's making it speed up or slow down and a part that's making it turn. We're going to spend a lot of time on that on one of the labs coming up. I can't remember if it's next week or the week after. Any questions about that? Okay. Yes. Oh, yeah.